This conference will now be recorded.
Is my screen visible to you, Deepa? Okay, so let us start. I think, is it visible and audible properly?
Yes, Ram.
Deepa, can you confirm once?
Yes, yes.
Okay, thank you very much. Yeah, we'll start now. So Deepa, we'll start today a new chapter. That is in NCERT textbook, it is 7th chapter, System of Particles and Rotational Motion. So it is very, very important and it has lot of good concept to learn. So today's class will be on little bit of introduction. Then we'll define few terms like what is called rigid body, external, internal forces, and how many types of motion a rigid body can have, all different types of motions. And we'll learn little bit about center of mass, like what is center of mass, what is the significance of center of mass, etc. We'll be learning today. So look, in the earlier chapters, basically 5th and 6th chapter, we were discussing laws of motion and its application, work, energy, power, those things we had discussed. And you know, Newton's laws of motion are actually derived on the basis of single particle. Okay, single particle. We'll define what is particle. Actually, particle is a point mass which has finite mass but no physical dimension, or in other words, size can be neglected. So those kind of things are called particle, like say a point. Particle is a point mass. And when Sir Isaac Newton derived these laws of motion, all were derived for particle. Particle means point masses. But what we have done, we have seen the same laws of motion we have applied for extended object. Extended object, that means which has multiple of particles, like a body like this, a bus. Okay, so I hope you remember we have talked about the motion of buses, and see motion of many other objects which are actually extended object. Extended object means they have really physical dimension. They are not point mass. They are not like that, not like a point. Okay, they have physical dimension. They have finite masses, and at the same time they have physical dimension like length, breadth, volume, etc. Okay, but still we have used the same laws of motion which are meant for single particle or point masses. We have applied those in case of extended object, and thinking that the same law can be applicable for extended object. So this is actually a crude approximation. So we have already learned the motion of various objects using the laws of Newton's motion, Newton's laws of motion, and it was actually a crude approximation of his of these laws, because these laws were actually meant for point particles or point masses. So it was crude approximation. So results will not be that perfect. Maybe things are approximately all right. But what is the actual motion of an extended body we'll be learning here. An extended body is actually composed of a number of particles, and when we have number of particles, how to deal with the motions. Those things actually we'll be learning here. And in this, actually the central concept will be the the new concept of motion of extended object. And here actually we will be talking about center of mass. Okay, center of mass. Here we'll be talking about center of mass. What is center of mass we'll be defining, but still I'll just tell you one thing. So center of mass is, suppose there is an object like this. So center of mass is a point in this object, or sometime maybe that this point can be outside of the object also. So center of mass is, I'm sorry, no, center of mass cannot be outside of the object. Center of gravity can be outside of the object. Okay, so center of mass, cm or com, sometime people write. So center of mass is a point in within the object, extended object, through which the whole mass, like at which the whole mass is concentrated. If the mass is capital M of this particular object, there will be a point inside within this object itself where the whole mass of the object is concentrated. Look, if we think any, like see like motion of any object in terms of center of mass, in terms of center of mass, then we can apply easily and without any confusion, any approximation, we can use this Newton's laws of motion. I'll repeat it. I hope you have understood, but still I'll repeat it. See, here we'll be defining center of mass of extended bodies. So what is center of mass? Center of mass is a point within the object where the whole mass is concentrated. Suppose this object has mass capital M. Okay, any shape of object, for any shape of object, we can calculate the center of mass approximately. So center of mass will be a point through which the whole mass is acting, or at which the whole mass is concentrated. Okay, and if we analyze the motion, or if we see, if we apply a force, any force on this object, we will think that the force is acting on this center of mass. And if we see the motion of center of mass, then the motion of the whole object will be identical as that, as the motion of the center of mass. And center of mass, as I said, center of mass is a point. So look, if we define the center of mass, or if we can find out the center of mass for any extended object, then we can use laws of motion for that center of mass. Okay, which will give you the clear picture of the motion of this whole extended mass. So this is how actually center of mass is generally defined for extended objects, and the motion of the extended object or system of particles will be analyzed by the motion of the center of mass itself. Okay, so this is the whole concept over here. And generally rigid object like motion of wheel, then motion of a symmetric or spinning top, and molecules, and maybe sometime iron bar, etc., will be taking as system of particles or rigid body. We'll discuss what is rigid body in the next transparency. So these are the kind of like objects, like you can take sometime rectangular bar of iron also, okay, rectangular bar of iron as a rigid body for discussion of. See, rigid body can have various type of motion, we'll see those. See, yeah, so these are, so let us learn first few definitions here. So I have already told what is particle, but still we'll repeat it. A particle is defined as an object which has finite mass but size and internal structure may be neglected. It is actually a point. It is actually a point mass. Okay, that is particle. Point mass is a particle. Okay. Now we'll see the definition of system of particles. System of particle is defined, or a system of particle actually is composed of a large number of particles. Large number of particles. So suppose you have an extended object, so you may have large number of particles within it, or large number of particles which is constituting this extended object. And see, all these particles, they interact each other. It is not like that they are inert or they don't interact with each other. It is actually they interact with each other. So system of particles, they interact with each other, and mostly in many cases as an approximation we take interaction between nearest neighbor. Okay, so a system is a collection of large of particle. A system of particle is a collection of large number of particles which mutually interact with each other. So this large number of particles, they interact with each other. So if you have an object of 5 particles, or this is called 5 particle system, so they will actually interact with each other. Interaction means they will exert a force, either electric force or electromagnetic force, or maybe mechanical force, anything. Okay, so they can have like this. Okay, so there will be various interactions among them. These are actually called mutual interaction or internal forces. We will see that. Now what is rigid body? Rigid body is a system of particles. So we have learned system of particles. It is a collection of large number of particles. And rigid body is a system of particles with definite and unchanging shape and size. What does this mean? We'll take up an example and see. Ideally, distance between different pairs of particles of a rigid body do not change. Actually, if you want to have like a rigid body, at least you should have 3 particles. Okay, this is how generally rigid body is defined. See, rigid body, suppose you have a particle which has three, like you have a rigid body or a system of particles which has particles, 3 particles. So suppose this is having mass m1, this is having mass m2, and this is having mass m3. They have distance between them r1 2. This is maybe r2 3 or 3 2, anything, and this is actually r3 1. Okay, they have these distances. Okay, according to the definition of rigid body, this body will be called, this system of particles will be called as a rigid body if the distance is like r1 2 between m1 and m2, distance between this m2 and m3 which is r2 3, and distance between m3 and m1 which is which is r3 1, or maybe you can take uh yeah, so these distances will not change with time and spaces. Okay, this will never change. So when these distances between any pair, distances between any pair does not, like distances between any pair do not change, then the object will be called, or system of particle will be called as a rigid body. And rigid body, since the distance between each pair do not change, the size will be always definite and unchanging. Size and shape will be definite and unchanging. Like if you have any shape of object, like you have a kind of rectangle like this. So there are four particles. So they have this rectangular shape, and suppose the dimensions are like, so this is 5 centimeter and this is 2 centimeter, whatever. So these length and breadth will not change. In fact, this distance will not change. Even this distance will not change. Okay. So then it is called rigid body. All right. Now we'll learn what is called mutual force. Sorry, internal forces. So internal forces, as I said, if you have object of three particles, suppose. So you look, this is M1, this is M2, and this is M3. So their distance, since it is a rigid body, their distance will not change. Okay. And see what is internal force. The internal force is the force between, like mutual forces between each pair. Mutual forces between each pair. See, maybe this guy, see M1 is giving a force, attractive or repulsive, whatever. That depends like how it is. Okay. So whether, okay, we are not going into that detail whether it is like attracting or repulsive. Let us say the force which the object point 1 is exerting on M2, mass M2. At the same time, the mass M2 will be giving a force to the particle of mass M1 as 2 1. Force exerted by 2, particle 2 on 1. And these forces are called mutual forces, and these are actually equal and magnitude, in equal in dimension and magnitude, like sorry, magnitude equal in magnitude, and direction will be exactly opposite. If you take the sum of all internal forces, F12 plus F21 plus F23 plus F32, these are mutual forces, and F31 plus F13, the sum of these internal forces will be actually 0. Okay. Sum of internal forces are kind of action and reaction. Kind of action and reaction. So these are internal forces we have somewhat discussed while discussing Newton's third law of motion. Okay. So internal forces are called, actually they are mutual forces. They are somewhat action and reaction. Okay. And sum of all the internal forces will be actually 0. That means what? That means these forces are actually not manifested, or they cannot manifest any motion of the object. So internal forces cannot cannot make any motion of the object, make any motion of the body. Okay. So internal forces cannot make any motion in the body, because sum of the internal forces will be always 0, because this these forces are actually equal in magnitude and opposite in direction. So they are kind of action and reaction. And when you take action and reaction, sum of action and reaction, this will be always 0. Okay. I hope uh, it is understandable. And then you might be thinking, what is the significance of this internal force? Actually, it has significance. It has a significance. These forces, internal forces, they are actually responsible for holding all the particles together to behave as a single object. Okay. So if they don't have this mutual interaction and repulsion forces, they cannot be together. Okay. They cannot be together. So mutual, these internal forces are responsible for holding all the particles to be as a single object, to hold all the particles together. Okay, that is the significance of internal forces. Now, what is external force? Actually, external force acted upon an object by some external agency. So, the force which is acted upon an object by external agency, some external agency is called external force. Suppose I have a rigid body, you are applying a force, you are just hitting the object with hammer, or you are pushing it, whatever. So whatever force is exerted by any external agency, like our hand or something else, so that force is called external force, and external force is responsible for making motion in the rigid body. This is responsible for motion. So external force is responsible for motion of any body. Obviously, external forces will see if more than one external force and in the equal and opposite direction they work or they act, then this does may not have any velocity, may not have any motion, but anyway, that is called equilibrium situation. In general, external force is responsible for the motion. Okay, so this is these are the definitions you should be knowing, and then we'll just go to learn like how many types of motion a rigid body can have. How many types of motion a rigid body can have. Okay, so that is our, just a minute. We'll see now how many types of motion a rigid body can have. Okay, just a minute. It is actually, yeah, it is already given animations. Okay, all right. Let us go with the slides. Okay, so yeah, there was some mistake in the slide, so I just corrected now. Okay, so now we'll see how many types of motion a rigid body can have. See, rigid body can have different types of motion. So we'll see one by one. First, we'll see a rigid body can have a pure translational motion. Pure translational motion. What do you mean by pure translational motion? Look, we'll see with an example. Let me just give you a simple example first, then I'll go to that example. Suppose there is a box, okay, there is a box, you are pushing the box, okay, you are pushing the box with some force, and when it is in motion with some velocity, motion, so when it is in motion, suppose I just consider few particles over here, maybe like this, okay, so this is P1, this is P2, and this is P3. So when an object is in translational motion, what happens? Every particle moves together. That means, see, when this you are pushing this box, it is not true that only P2 is in motion. Everyone is in motion. P1, P2, P3, all of them are moving together. So all particles move together. together. Okay, all of them moving together. Not only that, when this object, this box has a velocity v, all of them p1, p2, p3 will have v velocity. Okay, all of them will have v velocity. It is not like one particle is moving whereas the other particle is standing, or it is at rest. It is not like that. So in translational motion, that is such kind of a motion where all the particles of a body is moving together. All the particles are all the particle. This is not is they are all the particles. Okay, so every particle of a body is moving together, and each of them has the same velocity at any instant of time. See, the same thing is been shown here. This is also an example of translation motion. See, or translational motion or translatory motion. There can be many names. See, this is a block of mass, some block of mass m suppose, and it has many particles, as you know, this system of particles. And initially it was at the top here somewhere, okay, and then it is just sliding down the inclined plane. It is sliding down, as you see now. At some instant of time, the position of the sliding block is this, what you see. So the block is moving down the inclined plane, and look, when it is moving down the inclined plane, all the particles, like here it is shown p1 and p2, they are all moving together. They are moving together, and the velocity also the same as I have shown in case of plane, like translation motion. Okay, so this is actually the like one of the motion which a rigid body can have. Pure translational motion. Pure translational motion where all the particles move together with same velocity. Okay, now we'll see a pure rotational motion. So when we can have pure rotational motion, actually, see, if there is no translation, see, in case of pure, in this, see, pure translational motion means there was no rotation at least. So when we talk about pure rotational motion, obviously we have to fix the object somewhere. Okay, we have to fix the object such that it does not translate. It does not change its position. Translation means what? It goes from one point to another. Okay, it is changing the position. So for a pure rotation, you have to fix the object somewhere. So when an object moves around a fixed line, passes either through the object itself or a line outside the object. This type of motion is called rotational motion, and fixed line is called the axis of rotation. Let me give you the example. See, in this ceiling fan, what we see, ceiling fan actually it is not moving up and down, right? It is not moving up and down or sideways. It is not moving like that. Okay, this is ceiling fan. So what kind of motion you see? The blades are actually rotating. As you see, blades are rotating like this. Okay, blades are rotating. So rotation, whenever we talk about rotation, there will, see, the blades are rotating about some fixed axis. See, the axis is actually passing through the blade, like passing through this ceiling fan, or middle of the ceiling fan. You have this kind of thing, like you have a blade now like this, and another blade maybe like this, another blade maybe like this. Okay, like that. And you see it is fixed through this. Okay, so this line, so there is a line, fixed line through the middle. Okay, through the middle of the ceiling fan, and about that the blades are rotating or the fan is rotating. Okay, so in this case you look, the blades are rotating about a fixed line. So this kind of motion is called rotation, and the line, fixed line about which the blades are rotating is called axis of rotation. Axis of rotation. Not only line, obviously. So see, this is, I can take you through another example. This is actually potter's wheel. So where the potter, what he does, he keep the uh, soft clay, and it rotates. See, it rotates. The clay is rotated with actually this wheel. This is potter's wheel. This is potter's wheel. Potter's wheel. So clay is kept here on the wheel, and wheel is rotated with great speed. And see, it is rotating about a fixed line or axis of rotation which is passing through this clay itself. And out of clay, see, this nice pot has been made, and now the pot is actually moving with the wheel having an axis of rotation, and the axis of rotation through the pot. Okay, that means axis of rotation can lie within the object, and we will take, see, in these two objects, this is axis of rotation for both of them. Axis of rotation lies within the body, within the object. Okay, within the object itself. Now we can take another example where rotation happens, but the axis of rotation doesn't lie within the or goes through the body. So look here, you might be are experienced with this kind of playful incident, that you just tie a ball or a rock with a string and try to rotate about, like, rotate in a horizontal circle or vertical circle also you can do. You can see this this stone or the ball is rotating about an axis which is passing through your hand. So this axis of rotation is actually not passing through the object. So pure rotation is the motion where the object is actually moving about a fixed line or fixed point. Okay, or a line passing through a fixed point, and that fixed axis or fixed line can be passing through the object itself, or maybe that can lie outside the object. So in these three examples, as we can see, so the axis of rotation passing through this object for these two, and for this axis of rotation passing outside the object. Okay, we'll just learn few more things about rotation. See, when rotation happens, suppose this is a rigid body, it has many particles. We are taking some representative particles like P1, P2, and P3. So when rotation of the object happens, all the particles within the rigid body, what they do, they actually undergo a circular motion, undergo each of them undergoes a, so what it does, each particle within the object, first point, object undergoes a circular motion. Uniform circular motion we have learned already. Okay, circular motion. So, and this, see, the radius of the circles. See, circles are in the same plane. Okay, you can see they are in the same plane. Okay, they're in the same plane. In the same plane, they lie in the same plane. Okay, but radius radius or radii, it is radii are not same, are not the same. So they undergo circular motion with various radius, and this see the circular paths will be actually uh, in the same plane, but or maybe parallel. You can say parallel. The plane of the circles will be parallel to each other. Plane of the circle will be parallel to each other, and this radius actually depends on how much distance away the particles are situated from the axis of rotation. Okay, from the axis of rotation. And see, one more thing is actually the angular velocity, angular velocity, angular velocity that is omega for is same for all the particles, all the particles. Okay, all the particles. Whereas this will show you sometime else. Whereas linear velocities v is equal to radius of the circular path. They are moving in. Suppose this is r into omega. So this is general formula. So v is equal to linear motion is actually r into omega, and linear motion has actually direction of velocity along the tangent. At each point the linear velocity will be along the tangent to that point. Okay, like that. And this velocity is always constant for a particular orbit. This speed, this is not velocity, this is called speed. This is called linear speed. Angular speed is omega. Angular speed, that is same for all of them. See, this is angular speed, and v is linear speed is varying with their distance. Sorry, distance from the axis of rotation. Linear speed. So angular speed and linear speed, they are v is equal to r omega. They are related like this. So v is equal to, sorry, linear speed is equal to r into omega. This will prove later, r into omega, or maybe we have already proved this. So v is equal to r omega. So if r changes, so v1 will be r1 into omega, v2 will be r2 into omega, because their positions from the axis of rotation is different. So that's why linear speed will be different, but linear speed will be constant again for a particular orbit. Okay, so this circular path is called orbit. Okay, so these are few points. Another most important point is that when the axis of rotation, you can see this at z axis. So this axis of rotation is passing through the object itself. Then the the particle which are on the axis of rotation, they don't have any motion. See, this is having no motion. P3 no motion for the P3. And see, centers of the circles like C1, C2, these particles, they actually don't move. So the particles on the axis, they don't have any motion. Okay, so what we have learned during a rotational motion, pure rotational motion, of a rigid body, each particle they undergo circular motion, and center centers of each circle center of each circular path will be lying on the axis of rotation. So centers of this circular path will be lying on the axis of rotation. Linear speed is different for different particles, whereas angular speed is the same for all of the particles. So linear speed depends on the distance, how much distance away the particle is from the axis of rotation. And the points which are on the axis of rotation, they are not in motion. So these are few points. So these are all mentioned very nicely in NCERT textbook. So we can have see in rotation of rigid body about a fixed axis, every particle in the body moves in a circle which lie in a plane perpendicular to the axis of rotation. Okay, so that is what was about pure rotation. So in pure rotation, you don't have translation, only rotation you have. And in rotation, you can see some points can be, see in rotation, some particles may not move also. Particles may not move. So which are on the axis of rotation, they don't move, may not move. Okay. If the axis of rotation is going through the body, that's why I have written may not move. Okay. It could move if the axis of rotation is actually this outside the object, then each of the particle will be moving. Anyway, so now we'll see, we have learnt pure translation, pure rotation. Okay, there can be another type of motion which is called pure vibration. Pure vibration, this is not mentioned in your textbook. Vibration, this also can happen, like see if you have two uh yeah, so suppose this is a dumbbell, and so this dumbbell, if these two can move like this way and that way, so this motion will be called as vibration. Like see simple pendulum motion of a simple pendulum is kind of a vibration. Okay, so vibration, each object can have vibration, translation, and rotation. This kind of motions can be seen for any rigid body. Okay, so but we are not mentioning about pure vibrational motion. So there can be mixed rotational and translational motion as well. So if the motion of rigid body is a combination of rotation and translation, then the motion is called mixed rotational and translational motion. We will take up an example. See, suppose you have a cylindrical object, cylindrical object made of wood or metal, anything. You keep it here and you roll it. Rolling means what? It will be translating, or it will be moving down the inclined plane. At the same time, it will be rotating. Okay. So something which is rotating. So rolling motion of this rolling motion. Rolling motion is actually rotation plus translation. Rotation plus translation. Okay. So this is rolling motion. We can have in another example, like when you ride a cycle, what happens? Cycle, see wheel of the cycle or any motor car or anything. So they have rotational motion at the same time translation. They're moving forward, at the same time they're rotating also about the axle. Okay, about the axle. So this kind of motion is called rolling motion. And during a rolling motion, see, if we look this particular case, at any instant of time, if I consider point P4, which is periphery of the cylinder, and another point like this is at the bottom of the cylinder, which is in contact with the inclined plane P3, and P1, P2 within the cylinder. Now look, each of them, are they moving together? No, maybe P1 and P2 moving together, okay, together. Whereas your P4 is moving, not moving with this two. This is moving separately, okay. That means the velocities of these two, P1 and P2, will be different than P4. Or the speed, if you say speed is different for P4 than P1 and P2. Now look P3. P3 is actually at rest when any object is just rolling on a floor or inclined plane or whatever, like this. So this point will be with the ground, and for the time being, when it rotates, this particular point for an instant will be fixed to the ground. So this will be fixed to the ground, and or a stationary point, it will be stationary. This is a contact point with the ground, stationary, it will be stationary. So here also, while an object is having a rolling motion, a point which is contact with the floor or the inclined plane will be stationary. So here P3 is stationary, okay, or fixed. So this is how actually there can be mixed translation and rotation, which is called rolling motion. What is that motion? Rolling motion. Translation and rotation, both together. Now, see, there is a nice statement over here. The motion of a rigid body which is not pivoted or fixed to some way is either a pure translation or a combination of translation and rotation. Like, see, rolling motion, there is no fixed point, it is moving, right? So this is the example of rolling motion. No point is pivoted or fixed. No point of the object is pivoted or fixed. So then you can have either pure translation if there is no rotation, or mixed rotation and translation, which is called rolling motion. You can have these two motions, okay. If no point is fixed, no point is fixed or pivoted, okay. Now if any point is pivoted, point is pivoted or fixed or pivoted, then there will be a pure rotational motion, pure rotation, pure rotational motion, okay. Then it will be a pure rotational motion, okay. So we'll take up another interesting motion which is called precision, that is motion of a symmetric top. Let us see, you might be seeing this toy. This is actually a very favorite toy for any child. You might also have played with this. This is a top, spinning top. So the motion of spinning top is very, very complicated. You know why? The top, you look, the top is rotating by itself, okay. Not only that, when it rotates, the axis of rotation, that axis of rotation also moves around the vertical axis. See, if this is OZ, a vertical axis, so this axis of rotation of the top also will be moving, okay, around this, okay, around this axis of rotation. So axis of rotation will be moving around, if moving around the vertical with the ground and sweeping out a cone, like it will be making a cone kind of thing, okay. So it will move like this and it will make a cone kind of that, okay, cone kind of shape it will make. And the movement, see, you'll be able to appreciate if I show this, okay, this also. See, the axis of rotation changes, okay, time to time. This is once it is axis of rotation, some other time this will be the axis of rotation, this will be the axis of rotation, okay, this will be the axis of rotation. So the axis of rotation also change, actually moving, axis of rotation also moving around this vertical axis OZ. And in other words, you can say this axis of rotation actually sweeps a cone like this, okay. And this kind of motion is called precision. This kind of motion, when you have rotation and the rotation axis will be also in motion about about a vertical axis with fixed angle of inclination, okay. So in fact this will sweep a cone about a vertical axis. And this point of see, this point which is on the ground will be always fixed. It doesn't move. It can move also, so that will be more complicated. But if this doesn't move, if it is fixed, then it is called precision. So point of contact with the ground is always fixed. So this is actually spinning motion of a top. You might be thinking, sir, what are the use of learning this? Yeah, there are some points which you had to learn about various motion of rigid body. Okay, so now what we'll do, we have got 5 minutes, five five to maybe, yeah, 5 to 10 minutes maybe we'll take. So we'll just learn about center of mass and then we'll stop. Okay, so as you see, the center of mass is the key concept of this chapter. So please be attentive while learning center of mass. And we'll be seeing there will be various problem related to calculating center of mass of various shape and various size of object and various, yeah, so various objects. There will be problems in the competitive exam to find out the center of mass of various objects. So better to learn the center of mass very attentively. So what is center of mass? As we have discussed, center of mass of a body is a point where the whole mass of the body is supposed to be concentrated. And this is actually defined, center of mass is defined for describing translation or translatory motion. Translatory motion. You know, when you have an object like this, okay, so this is symmetric object. So generally for symmetric object, center of mass will be at the center. So center of mass is this point. And whenever this object is actually acted upon by any external force, this generally generally act on the act on the center of mass. And when this applied force is acting on the center of mass, then it will have translation motion, translatory or translation null, whatever you can say, translatory motion. When translation motion will be there, when the applied force will be, like, line of action of force will be passing through the center of mass cm of an object. Okay, let us take a simple example. Suppose I have hammer like this. Okay, this is a hammer, kind of hammer. Okay, look, it goes like this. Okay, so suppose this is an hammer. So center of mass is somewhere here. If you apply the force in this line, okay, so if the force, center of force, okay, this, I'll clean this everything, then I'll take. Suppose you have an hammer. This is kind of a hammer like, okay, thing. Okay, the center of mass will be actually somewhere here. Okay, suppose somewhere here at the center of mass. So when you apply a force like this, okay, so apply force like this, so the line of action of force goes or pass through the center of mass. Okay, so in this case, you know what will happen. This this hammer will be having a translational motion. It will move from here to here. Okay, it will move from here to here. But suppose the force is not, line of action of force is not going through or passing through the center of mass. What will happen? It will have actually a rotational motion. Suppose the force is applied like this. You know what will happen? This hammer will be actually rotating about, rotating. See, if you push like this way, so it will rotate about the center of mass. Okay, the hammer will be actually rotated about the center of mass like this. So it will it will have a rotational motion. It was like this, so it is now like this. So center of mass concept is very important. So whenever we apply an external force for translational motion, the line of action of force should pass through. See here, the line of action is perpendicular to the center of mass, or maybe, yeah, we can say just it is not going through the center of mass. So in this case, you have rotation with rotation about cm, center of mass. Okay, about center of mass. Okay, so yeah, this is about center of mass. Now we'll go to find out numerical expression or mathematical expression for center of mass. So expression for center of mass, for center of mass. Okay, so let us take very simple configuration of two masses. Okay, and two masses, as you see from this figure, two masses are situated on the x-axis, okay, of the coordinate system. See, m1 is situated at x1 distance away from the origin, and mass m2 is situated, this is this one. Okay, m2 is situated at x2 distance away, x2, this is up to this. So this is x2 distance away from the origin. Now how center of mass is cm. If the center of mass coordinate is x, then it is defined like this: m1 x1 plus m2 x2 divided by m1 plus m2. So this is actually the definition of center of mass coordinate. This is called, since the particles are in the same line, so it has only one coordinate. So this is called center of mass coordinate. Center of mass, or center of mass coordinate. Okay, center of mass coordinate or position of center of mass. Okay, center of mass coordinate or position of center of mass. When the two objects are on the same line, that's why it has only one coordinate. So position of center of mass of cm. Okay, now look, this can be actually, it is actually can be told, see, this is m1 plus m2, so the whole mass of the two objects, okay, or the summation of the mass of the two objects. So this center of mass can be, see, cm can be uh, called as mass weighted mean of positions, right? Mass weighted mean of positions, okay, positions. The positions are x1 and x2. So mass weighted means it is divided by the total mass. And look, now we can have another interesting result from here. If m1 and m2 are equal, if m1 and m2, the masses, two masses are equal, then what we get, if m1 and m2 equal to m, see, x will be x1 plus x2 by 2, okay. So this is actually the mean position of the two objects, see. So the center of mass will be, if the object, if the two objects are having same mass, then center of mass is situated at the midpoint between the two objects. So if the masses are equal, then the center of mass is at the middle of the objects, okay, or masses, at the middle of the masses, okay, at the middle of the masses, okay. So this is how this we had taken for simplicity two objects, okay, two object system. But this can be extended to any number of, this formula can be extended to any number of systems. So we have got for two systems m1 x1 plus m2 x2 divided by m1 plus m2. This is a general formula. So this can be generalized to any number of particle systems. So two particle systems we have taken. So if there are n number of particles, if there are n number of particles with their corresponding position coordinates, and suppose all of them are on the same axis, then look what we can write. Center of mass coordinate can be written as m1 x1 plus m2 x2 plus m3 x3, like that it goes up to m1 mn xn. And in the denominator also there will be the summation of m1 plus m2 plus m3 dot dot, it goes up to mn. See, this expression can be written in a very short notation. I'll first write the notation and then explain. So you can write this notation as this. The whole of this sum can be written as this way. Suppose this is mi xi, where I goes from 1 to n, if there are n number of objects. In the denominator also we can write mi, okay, where I goes from 1 to n again here, okay. I'll write it clearly. So generally you can write in this notation, I goes from 1 to n, so mi xi divided by summation over mi, where I goes from 1 to n again, okay. So this is called, this notation is called summation, okay. So today we'll be stopping it here. So we had taken only two objects. We'll see next day if we have multiple objects, like if there are see more than two objects and they are not in the same line, they are in some plane, suppose in the xy plane x. So the see, this is m1 particle, this is m2 particle, maybe two particles, and another particle here maybe m3. Okay, so these are actually, they have both x1 and like x and y coordinate. So in that case, how to write the center of masses and how to arrive to vector notation of the center of masses, we will see in the next class, and we will be calculating center of mass for few representative object in the next class. Okay, so with this I'll stop it here. Deepa, if you have any question, you can ask me now. I hope you have understood what is the motivation of this chapter from the introduction part, what is called rigid body, and what is called system of particles, what is the center of mass. This concept have you learned today? Yeah, Deepa, you have any doubt from today's class? You can unmute and say, or maybe you can write in the chat box also. Okay, so if you don't have any questions or any doubt, I'll stop it here. Okay, everything clear? I have got your message. Okay, Deepa, bye for today. We'll meet again on Thursday with the rest of this center of mass concept. Okay, bye for today.